Section: Introduction. In this section, we discuss how deploying large language models, or LLMs, can be quite costly, not just in terms of the financial aspect but also considering the environmental impact. Specifically, running these models on specialized hardware like GPUs or TPUs during the inference phase contributes to a significant portion, around 80 to 90%, of their total carbon emissions throughout their lifecycle. The process of generating responses from these models, especially in a step-by-step or autoregressive manner, is primarily limited by the speed at which data can be moved between the model's memory and the processor. This is because the model needs to access large amounts of data quickly, which becomes a bottleneck. To tackle these challenges, various strategies have been explored. These include methods like block parallel decoding, speculative decoding, using a mixture of experts, improving the architecture of the models, and classical techniques such as distillation. However, despite these advancements, the process remains predominantly constrained by memory access speeds, indicating that there's still a lot of room for making these models faster and more cost-effective. Interestingly, for inputs of typical length, for example, less than 2,000 tokens, and even in models with up to a billion parameters, the softmax and feedforward, FFN, layers are found to be the main contributors to latency, accounting for more than 90% of it. Therefore, our work primarily focuses on optimizing these two components. Recent studies have shown that LLMs exhibit a certain level of sparsity, or redundancy, which seems to increase with the size of the model. For instance, it has been observed that the activations in the feed-forward layers, especially those using ReLU activation functions, are very sparse. To put it simply, when processing an input, only a small fraction of the weights in these layers contribute to the output. This sparsity can be further increased to less than 5% non-zero values by employing specific techniques during training. Given this background, we aim to answer whether it's possible to efficiently and accurately compute only the most significant elements of the softmax outputs and FFN activations on hardware accelerators. The challenge lies in identifying these top elements without having to fully compute the layer's outputs, and then efficiently gathering these elements for further processing. In our contributions, we introduce methods to address these challenges, significantly improving the inference speed of autoregressive LLMs without compromising on quality. We propose an approximate method with high recall for estimating the top elements in FFN and softmax layers, which, despite being an approximation, does not result in performance loss thanks to its high accuracy. This method, which we call HiRE, allows for a more efficient computation by predicting which elements will be most significant. Additionally, considering the distributed nature of LLMs during inference, we introduce a distributed approach to approximate the top elements across multiple devices, which avoids the need to centralize data before processing. This method significantly reduces the computational overhead. For the softmax layer, focusing on the top few outputs allows us to achieve a notable improvement in latency without losing quality. Similarly, for the FFN layers, we propose a method to handle the sparse activations more efficiently by grouping them, which improves memory transfer speeds. We also explore ways to further increase sparsity by leveraging the overlap in activations across different inputs. Combining all these approaches, we achieve a substantial reduction in latency, making the models much faster compared to using a fully dense approach. Our work not only demonstrates the effectiveness of these methods but also highlights the importance of optimizing for high recall and promoting group sparsity to achieve significant improvements in inference speed on hardware accelerators. In the following sections, we will delve into related works that have inspired our approaches, explain our key ideas in more detail, present our experimental setup and results, and discuss additional findings in the appendix. Throughout our discussion, we use standard notation to differentiate between scalars, vectors, and matrices, and to denote specific operations and restrictions applied to these mathematical entities. Section Summary. In this section, we focus on the challenges associated with deploying large language models, LLMs, particularly in terms of the significant costs and environmental impact involved in running inference. We delve into the memory-bound nature of generative LLMs, highlighting the dominance of autoregressive next token generation in driving latency and cost, and explore techniques such as sparsity in feed-forward (FFN) layers and top K computation in softmax layers to improve efficiency and reduce latency. Our proposed approaches, including high recall approximate top K estimation (HiRE) and distributed approximate top K (DA top K), aim to enhance the inference latency of autoregressive LLMs by efficiently estimating top elements in FFN and softmax layers, showcasing substantial improvements without compromising quality. Section: Related work. In this section, we delve into the background and the innovative concepts we're introducing in our work, HiRE. Let's start by discussing the related work and how our approach stands out. Firstly, we've observed, like many before us, that large language models, LLMs, tend to have sparse activation patterns, especially when using ReLU activation functions. Previous studies have shown that ReLU can perform just as well as other activation functions like JLU, prompting a reconsideration of its use. While there have been efforts to leverage this sparsity for quicker inference, these attempts often compromise on quality because it's challenging to predict activation patterns precisely. However, we've discovered that by accurately estimating which activations will be non-zero, we can maintain the quality of our model's output. This is because we can compute exactly for the activations we predict to be non-zero, and it doesn't matter if some of these predictions are incorrect. Our work introduces several novel strategies, such as using very small groups for group sparsity, a common dense path, exploiting overlaps in activation across tokens, and a distributed approach to gathering weights. These innovations are crucial for enhancing efficiency without sacrificing accuracy and for applying our methods to larger scales. In terms of sparse attention, there have been attempts to simplify the all-to-all attention mechanism to a sparser form. We believe that, similar to our approach with activation sparsity, accurately predicting which attention weights will be non-zero and computing exactly for these can avoid any loss in quality due to sparsity. From a hardware and systems perspective, there's been progress in executing sparse operations efficiently on GPUs and TPUs. However, unstructured sparsity often doesn't perform well on these platforms. Our work demonstrates that TPUs can efficiently support group-structured sparsity, even with relatively small group sizes, without compromising on the quality of pre-training or downstream tasks. Mixture of experts, MO, models represent an extreme form of structured sparsity, where the group size is significantly large. These models have been explored for their training and inference efficiency but are notoriously difficult to train due to the need for a gating mechanism and ensuring equal token distribution across experts. We find that using smaller group sizes or experts simplifies training, especially when incorporating a top K operation. Additionally, we explore various complementary approaches to enhance inference efficiency in LLMs, such as model compression, quantization, and speculative decoding, among others. Now, let's get into the main ideas of our work. We focus on the softmax and feed-forward (FFN) layers of a transformer model. The softmax layer takes an input vector and outputs a vector of probabilities across output classes, where we're particularly interested in accurately estimating the top K probabilities. The FFN layer, on the other hand, processes the input vector through an activation function and outputs another vector, where only a small percentage of activations are non-zero for certain activation functions like ReLU. We introduce a sparse version of the FFN layer, where we explicitly perform a top K step to further reduce the number of non-zero activations without losing quality. This approach can significantly speed up both the softmax and FFN computations by focusing on the most relevant activations. Our goal is to design an efficient mechanism for these computations that outperforms the standard method of computing the full matrix vector product followed by selecting the top K entries. This efficiency is key to speeding up inference in large language models without compromising on the quality of the results. Section Summary. In this section, we introduce the main ideas behind HiRE more rigorously. We focus on the sparsity of activations in large language models, arguing for the use of ReLU activation functions for comparable performance and efficiency. Additionally, we discuss structured sparsity in attention layers, hardware support for efficient sparse operations, and complementary approaches for speeding up inference in large language models. Section: Theoretical proxy for quantifying efficiency. In this section, we discuss a theoretical approach for measuring how efficient our algorithm is, especially when it comes to decoding with small batches. This process is mainly limited by memory, meaning the time it takes to move the model's parameters between different types of memory in the device, like from high bandwidth memory or RAM to cache, is what mostly slows down the inference. To better understand and quantify this, we look at the number of effective parameters, which we measure in bytes, used by an algorithm for its computations as a way to gauge its latency. We call this measure PS. For instance, our baseline method, which first calculates a specific function of our input vector and then selects the top k elements, has a PS value of 2 times d times L because it involves a matrix of size d by L, stored in 16-bit floating point format. Moving on, we introduce the main concepts behind HiRE and how it applies to certain layers in our model. The essence of HiRE is to use an approximate, smaller version of a matrix, which we denote as Z approximately. We first use this approximation to calculate a function of our input vector, select a set of top k elements for some k greater than k, calculate the function again but only for the selected indices, and finally perform the top k operation on this result. We provide both a pseudocode and a diagram to explain HiRE. It's clear that as long as the top k indices from the original calculation are included in our set of top k elements, HiRE will work efficiently. If Z approximately is significantly smaller than the original matrix and if K is much smaller than L, then HiRE will be much faster than the standard method. We consider two approaches for choosing Z approximately. In the first approach, HiRE LR, we use a low-rank matrix that is the product of two smaller matrices. This significantly reduces the PS value compared to the baseline, especially since we can choose the rank to be very small, which has the potential to greatly reduce latency. This approach requires training the approximate matrix either end-to-end or by decomposing the original matrix. In the second approach, HiRE-Q, we use a version of the matrix that has been aggressively quantized, for example, into 4-bit integers. This also reduces the PS value compared to the baseline, but without the need for training since we can apply a standard quantization routine to the original matrix. However, the potential for reducing latency is somewhat limited due to the nature of quantization. We also note that combining both HiRE LR and HiRE-Q could lead to further improvements in inference latency. Section Summary. In this section, we introduce a theoretical proxy for measuring efficiency in autoregressive decoding, focusing on the memory-bound nature of small batch sizes. We use the number of effective parameters in bytes as a proxy for latency, showcasing how different approaches like HiRE LR and HiRE-Q can significantly reduce inference latency by choosing smaller, approximate versions of the matrix Z. These methods offer potential latency gains by either using low-rank matrix factorization or aggressive quantization, with the possibility of combining both for further improvements in inference speed. Section. Begin, Algorithm. %latex2 HTML id marker 980 caption. Pseudocode for text RM, H, S, $. Output $overwrite arrow, Y, $end, algorithmic, end, algorithm. Very large models do not fit on the RAM of a single GPU, TPU, so for serving such models, the parameters of the model are usually distributed on a cluster of multiple devices. In this case, using HiRE algorithm, as is leads to large costs in communication. To mitigate the communication costs, we modify HiRE to use distributed, approximate top $k computation. The pseudocode for the resulting algorithm is given in algorithm. We will now present the application of algorithms and to make softmax and FFN layers more efficient. In this section, we discuss how to serve very large models that cannot fit into the RAM of a single GPU or TPU. Typically, the parameters of these models are spread across multiple devices in a cluster. However, Using our algorithm, HiRE, in its original form for such distributed systems incurs high communication costs. To address this, we've adapted HiRE to perform distributed, approximate top K computations, which significantly reduces these costs. The details of this adapted algorithm are outlined in the provided pseudocode. We then explore how to apply this algorithm to make the softmax and feed-forward neural network, FFN, layers more efficient. Specifically, for the softmax layer, since we're primarily interested in the top K logits, we can use our algorithm to compute these more efficiently. We achieve an approximate version of the weight matrix, W, through quantization and then obtain a low-rank approximation of this matrix at a relatively low cost. For the FFN layer, we recall that we can compute the top indices of K using HiRE. Although this approach is theoretically more efficient than a straightforward computation, the efficiency gains are limited by the inefficiency of transferring parameters across different memory hierarchies. This is where our key insight comes into play. Using a group sparse structure significantly improves the efficiency of parameter transfer. We demonstrate this by dividing the hidden units into groups and then computing an approximate group activation. This method not only improves memory transfer efficiency but also allows for a more efficient computation of the top indices in both single and multiple device settings. Furthermore, we propose methods to enhance sparsity by exploiting the overlap in non-zero activations across tokens. We introduce the concept of static and dynamic activation overlap. For static overlap, we augment the sparse FFN layer with a dense path of neurons that are activated for all tokens. This approach allows us to reduce the number of non-zero activations in the sparse part of the layer. The feed-forward layer is thus composed of two sets of hidden units, with the first set being used in a dense manner and the second set in a group sparse manner. By implementing these strategies, we aim to improve the efficiency of serving large models across multiple devices, reducing communication costs and enhancing the overall performance of the system. Section Summary. In this section, we introduce modifications to the HiRE algorithm to reduce communication costs when distributing large models across multiple devices. By applying these modifications to softmax and FFN layers, we achieve more efficient computations by focusing on the top K logits. Additionally, we propose enhancing sparsity by leveraging static and dynamic activation overlap, such as augmenting sparse FFN layers with a dense common path to further reduce non-zero activations. Section: Dynamic Overlap. In this section, we delve into the concept of dynamic overlap. To enhance efficiency while generating a larger number of samples for the same query, for instance, to rank these responses and select the best one, we initially calculate the scores for the latest token from each of the samples. We then take the union of these scores across all samples on the first line of our algorithm. Moving on to experiments, we evaluate the performance of our model, HiRE, showcasing its ability to reduce inference latency. Regarding training details, we largely adhere to the previously described training setup, including the dataset and optimizer used. Our experiments were primarily conducted on a model with approximately 1 billion parameters, which we refer to as the 1B model. The term, model dimensions, refers to the size of the representations within this model. For the HiRE FFN component, after an initial pre-training phase of the 1B model for a significant number of steps, we continue pre-training it for an additional similar number of steps. During this phase, we apply a group sparse top K operation on every other feed-forward network, FFN, layer, specifically the odd-numbered layers, to achieve group sparsity. For a fair comparison, we also continue pre-training for the same number of additional steps without the top K operation to establish a baseline model. While the exact computations are performed using 16-bit floating point numbers, the approximate computations in HiRE are carried out using 4-bit integers. In the case of HiRE softmax, we apply it to either the baseline model or the model with group sparse FFN layers, exploring different methods for approximate computation. For low-rank approximation, we train a matrix with cross-entropy loss, choosing the rank to be a quarter of the model dimensions. For quantization approximation, we perform the softmax computation using 4-bit integers. We also explore combining both low-rank and quantization approximations. We refer to the model with HiRE applied to both softmax and FFN layers as the full model, while the application of HiRE softmax to the baseline model is denoted as the softmax model. In our evaluation, we assess the performance of the different models in terms of both quality and inference latency. We measure quality using evaluations on the pre-training dataset as well as on multiple downstream datasets. These datasets allow us to comprehensively evaluate the model's performance across a variety of tasks, each designed to test specific capabilities of large language models. For our pre-trained base models, we perform one-shot evaluations on all datasets. For machine translation, we use tasks from WMT14 and WMT22. For the superglue benchmark, we engage with multiple tasks, with a detailed list available in the appendix. Our question-answering evaluations utilize datasets such as SQUADV2 and TriviaQA, among others. We also evaluate the model on additional tasks to assess common-sense reasoning, ranking, and textual entailment capabilities. Our evaluation metrics vary by task, including exact match for question answering, except for TIE-DIQA where we use F1 score, accuracy for discriminative tasks, and character n-gram F-score for machine translation. We report the macro average of task metrics in our downstream evaluations. To evaluate inference latency, we use a single TPU-v5e device with a batch size of 1, generating one full response per query. We also highlight the significance of DA top K in scaling to multiple devices by presenting results for a configuration of 4 TPU-v5e devices. We report speedups by measuring the number of response tokens generated per unit time step. Section Summary. Dynamic overlap. In this section, we conduct experimental evaluations of HiRE to showcase its effectiveness in reducing inference latency. We train a model with approximately 1 billion parameters, denoted as the 1B model, and apply HiRE FFN by modifying specific layers for group sparse top K operations. Additionally, we implement HiRE softmax with low-rank and quantization approximations, evaluating the models on various tasks like machine translation, superglue benchmark, and question answering to assess both quality and inference speed. Section: Results. In this section, we discuss the results of our experiments with HiRE softmax. We compare HiRE applied to the softmax layer of the base model with the original dense model. We found that both HiRE-Q and HiRE-LR speed up the process by about 1.16 times compared to the baseline, while maintaining nearly the same accuracy for predicting the next token in the pre-training dataset. The accuracy for downstream tasks is also very close to the baseline, within 0.2%. Interestingly, when we combine HiRE-Q and HiRE-LR, we achieve a speedup of 1.22 times with less than a 0.5% drop in overall accuracy. Moving on to HiRE FFN, we compare the performance of HiRE FFN alone and the full HiRE approach, which applies modifications to both the softmax and FFN layers, against the original model. Similar to the softmax layer, combining HiRE-LR and HiRE-Q for the FFN layers results in up to a 1.47 times reduction in latency, while keeping the pre-training and downstream evaluation accuracy almost the same. When it comes to deploying large language models, LLMs, in latency-critical applications across multiple devices, the standard implementation of HiRE is not optimal due to the overhead of identifying the top K activations across all devices. To address this, we proposed a distributed version of the top K operation, named DA top K. This method first performs a top K divided by D operation on each of the D devices and then combines these activations to approximate the top K. This approach has improved latency by 2.27 times compared to the standard HiRE implementation, with a comparable quality across downstream tasks. We also delve into why high recall estimation is important. By defining recall as the intersection between the set of elements computed using the approximate matrix and the original matrix, we observed a systematic increase in recall with an increase in K for both higher LR and higher Q. This trend is also evident in the FFN model, where evaluating different K and K pairs shows that higher recall correlates with improved pre-training metrics. The importance of learned projections in higher LR is also highlighted. Unlike higher Q, which is straightforward to implement without training, higher LR can potentially offer larger latency improvements but requires retraining. We investigated whether random projections could be a substitute for learned ones and found that random projections could lead to a significant reduction in downstream evaluation accuracy, justifying our approach of using learned low-rank projections. We also explored the impact of the location of sparse layers within the model. Our results so far have only modified the odd FFN layers to be sparse, while the rest remain dense. We found that making all layers sparse significantly reduces accuracy, indicating that the placement of sparse layers affects overall performance. Identifying the optimal configuration of sparse layers is an interesting avenue for future research. Lastly, we present our findings on a common path to further increase activation sparsity. Our technique successfully enhanced dynamic sparsity by 2%, which in turn reduced latency by about 6%, all while maintaining accuracy. Additionally, we explored the potential of exploiting activation overlap for generating multiple diverse responses to a single query. Our empirical evidence suggests that these responses share a significant overlap in their non-zero neural activations, which can be leveraged to increase effective sparsity in FFN layers, as shown in our experiments. Section Summary. In this section, we compare the higher softmax and higher FFN models with baseline models, showing that combining higher Q and higher LR can lead to significant speedups with minimal accuracy loss. Additionally, we introduce a distributed version of the top K operation to optimize latency when deploying LLMs on multiple accelerator devices. The importance of high recall estimation is highlighted, especially in the context of learned projections in higher LR, where using random projections can lead to accuracy reductions, emphasizing the significance of learned low-rank projections. Section. Broader impact statement. In this section, we discuss the broader impacts of our work. We believe that by using HiRE, we can make the process of running large models more energy efficient. Additionally, there are broader societal implications as making these large models more accessible could have various effects. However, we don't think there are any specific consequences that need to be emphasized in this discussion.